of 128 as my base, and this will make a lot more sense when we get into subnetting. So please, if you're confused by this, don't worry. This is all theory right now. When we get into subnetting and we get hands-on, it'll make a lot more sense, I promise you. So let's say we have ones and zeros here. If we have a 1 for each of these sections, and I'm going to space this out again as best as possible, it's not pretty. But if we have a 1 for all of these, this equals 255. Why does this equal 255? Well, you take this, and all these numbers add up. 1 plus 2 plus 4 plus 8, all this adds up to 255. So let's say if we didn't have all the ones and zeros, we had just some ones enabled, like these last 3 here. Okay, well, this would equal 7, because we have 4 plus 2 plus 1 equals 7. So our first number, or whatever number this applied to in the octet, would be 7. So if we had 7.7.7.7, it would just be this numbers repeating over and over. These numbers repeating over and over, right? So be 0.0000111 dot 0.0000111, and so forth. So this is kind of what it looks like behind the scenes, because again, a computer is just ones and zeros. We're all binary. So what we're going to do is we're going to close this out. And we're going to talk a little bit of other theory when it comes to this, and why INET or IPv6 and why IPv4. So let's close this and let's talk about IPv4. So I'm going to bring up a calculator. And with IPv4, we have these 32 bits. So what we can do is we could take 2 to the 32nd power, and this is the possible amount of IP addresses that we could have. So we have somewhere in the 4 billion range of IP addresses. Well, spoiler alert, we don't have only 4 billion people on Earth, right? We're up to 7 something billion at this point, and all these IP address spaces are gone. So IPv4 has been around since 1981. Nobody thought we were ever going to use all these addresses. Computers weren't really a thing. Who knew that we were going to want all these addresses? And, these companies started buying them up, and they started buying them up in large chunks. And then they sold those to ISPs, and then ISPs sell those to you. And so these IP addresses have been gone for a very, very long time. And chances are when you have an IP address and you get this IPv4, you're only going to get one. If you're a corporation, you might buy more. But we've run out of IP address space. There's just not enough to go around. So the theory is, okay, let's come up with something different. Let's come up with IPv6. Now, this hexadecimal is actually in 128 bits, which makes things just a little bit longer and adds quite a bit. So let's take this 2 to the 128 power, and we get a number that I cannot tell you how to say. Not even going to try, but I can guarantee you that in our lifetime, we will never use this address space. So we've come up with the solution of IPv6, but nobody really uses it. IPv6 is just a thing that's there, but when we get IPv6 addresses assigned, but still to this day, everybody's using IPv4. Well, how is that possible if we're using IPv4, but we're out of address space? Well, think about this. We're using something called NAT, which is Network Address Translation. Now, let's think about your network. So you might have a cell phone or computer or multiple devices. My network has at least 20 devices on it. I've got cameras, I've got multiple cell phones, smart TVs, everything that connects to my internet gets an IP address. And that's 20 IP addresses right there, right? So let's say I have 20 devices, that's 20 IP addresses. Am I taking up 20 IP addresses out of that 4 billion? No, we're actually using something called Network Address Translation, or it's called NAT for short. And we'll talk about this again when we set up our actual lab. But with NAT, what we're doing is we're assigning these private IP address spaces. So we've got this 192.168.57.139. Now, if you've ever seen a IP address before and you've been on a network, good chances are it probably started with 192, or maybe it started with a 10 dot or something along those lines. And that's because those are private IP addresses. So anything that starts with 192.168 is not an IP address that is going to be out in the interwebs. It is going to be an IP address that is only known to you. These are called private IP addresses. So because we use these private IP addresses, we can pass them out through what is called a public IP address. Now, to make better use of this, let's go out to Firefox, and I've already got a tab open. So I went to Google and I just said private IP addresses, and I clicked the second image here because I think it's a great image. So if we look at this, there are classes of IP addresses, private IP addresses. Now, there is a class D and E. We're not going to worry about those. The big three are class A, B, and C. If you know these, you are good to go. So if we look at class C, this is what the most common household and small business use. So we see it starts with the 192.168.0.0. So the 192.168 are constant. If you see a 192.168 address, you can guarantee yourself that that is a private IP address space. And then we have the range of changing this number between 0 and 255 and this number between 0 and 255. Why 0 to 255? Well, that'll all make sense when we get into subnetting. But what that allows us to do is have a large number of networks here and a small amount of hosts. But for a regular user like you or I, or a small business, 254 hosts is pretty good. I mean, I'm only using like 20 in my household. So the most common household is probably using this 192 address. But what about a big business, right? Something huge. Okay, well, they might use a 10 address because a 10 address frees you up to anything after this 10 is private. So 10.1, 10.1.1.1, whatever you want to put in here, up to 255 on each octet makes for a small amount of networks, but a large amount of hosts. Okay, and don't worry about the host versus network thing. Again, subnetting, we'll talk about that. It'll all make sense. But just imagine the amount of hosts that you can put in here with this wide range. So because of this, you'll see larger corporations using 10 addresses. You'll also see a lot of corporations, even small businesses, using 10 addresses. The matter of fact is, as long as you have this private IP address, you're good to communicate across your network. So any IP address outside of these and the loopback here are free game for the public address space. They're probably already owned, and you purchase those or rent those really from your ISP, your internet service provider. So going back to this thought, we have a class C address. My network's class C, 192.168.57.139 here. So it falls into that class C. I've got all these devices on this 192.168 network. All these devices are talking out of one IP address. That is my public IP address. That is what I rent from my ISP. And all of this network traffic goes out one IP. So this is how we have achieved or solved the issue of running out of address space without having to use IPv6. Not that there's anything wrong with IPv6. It's not pretty. I mean, it's way easier to type this stuff in than it would be to type something like this in. But at the same time, this is how we've solved it. We're able to still use IPv4 in mostly all networks, and we are able to communicate out with this quote-unquote IP address shortage. So hopefully that makes sense. We're going to build upon these concepts. Again, IPv4, IPv6 IP addresses are layer 3 protocols. Layer 3 is a router. So when we route traffic, we route via an IP address. So we're going to build upon that as well as we go in. Hopefully this is all just a refresher to you. So that is it for this video. I'll go ahead and catch you over in the next one. All right, so we're going to move down a layer here and talk about layer 2. So remember, IPv4, IPv6, IP addresses as a whole, that is layer 3. We're talking about routing. Here in layer 2, we're going to be talking about a MAC address or a physical address. Now, MAC stands for Media Access Control, and that is identified here in our ifconfig as this ether here. So we can think of this as our physical address and a way that we communicate when we are using switches. Switches communicate over this physical address. This is kind of how they know what device is what. So what we say here is if we have a device, say you just built a computer and you're installing your network interface card or your NIC, you're going to plug that in and you're going to have a MAC address for that NIC. Your cell phone, that's going to have a MAC address. Anything that's using a network interface is going to have a MAC address. So these MAC addresses are important because they utilize layer 2 or switching, and they are how we communicate over switches. Now, there's something to be noted briefly about MAC addresses. Now, MAC addresses have identifiers. So as you can see here, this MAC address has 6 different pairs of 2, right? And what we can do is we could take the first 3 pairs and we can just copy this, and we can go out and we can try to put it into a MAC address lookup. Now for this one, this is just going to be VMware. I'm not sure if it's actually going to come up, but I'm going to go ahead and paste it and see what happens. And you can see that the vendor actually shows up as VMware. So the first 3 pairs here are identifiers, and we can identify what we're up against. If you've ever looked in your house and you've looked at your network and you're trying to find a device and you see the IP address, but the IP address doesn't really help you identify it. You might see something along the lines of a MAC address because your home device, say your router, might also be what's called a layer 2/layer 3 device, meaning it's doing switching and routing for you. And it'll also know the MAC address of that device. So you can take the first 3 pairs here, put those into the Google machine, and see if you can identify what that device is. So if I was unsure, this didn't have a host name or device name, and I could just reach out and say, okay, well, let me look these up. Maybe it'll give me an inkling. It's not going to tell me the exact device, but if I know it's running VMware, then I can say, oh, that's my host machine running. Or if it's related to like Texas Instruments or something, maybe I know that device in my house. So this is just a quick way to look up devices and know about them. The other option or other thing that you need to know here is just that, again, MAC addresses, layer 2, related to switching. I'm just trying to repeat this and get this into your head. So that's all we need to know from this lesson. And we're going to go ahead and I'll catch you over in the next lesson. All right, so now we're moving into layer 4, which is the transport layer of the OSI model. And we're going to talk about what is TCP and what is UDP. So we'll type that in here, TCP versus UDP. So TCP is what is known as the Transmission Control Protocol. And you could think of that as a connection-oriented protocol. And we also have UDP, which is the User Datagram Protocol. And this is a connection-less protocol. So when we have these 2 protocols, one is best suited when it comes to high reliability. That's TCP. TCP is connection oriented. We want to make a connection, we need high reliability. So you can think of something like a website, which is HTTP or HTTPS, or you can think of something like SSH or FTP, the file transfer protocol. Those all utilize TCP. When you think about UDP, you might think about something like a streaming service, that's connectionless, or DNS is connectionless, or voice over IP is connectionless. And when this comes into the importance of scanning is super important. We're going to be scanning both TCP and UDP as a penetration tester, and don't worry about scanning right now. When we get into the scanning section, this will make a lot more sense. But we need to know what TCP and UDP are and define them broadly. So the most commonly used protocol that you're going to be scanning is going to be TCP. Now, TCP works on what is called a 3-way handshake. Now, if we look at the 3-way handshake, it's going to look something like this. We're going to first send out a SYN packet, and then we're going to receive back a SYN ACK packet, and finally, we're going to send an ACK packet. Now, how does this work? Now, you could think of this as an interaction. So let's say you have a friend or a neighbor, and you go to your neighbor and you say hello. That's a SYN. Now, SYN ACK is going to be the response. It's going to say, hey, SYN, I acknowledge you. That's your neighbor waving hello back. And then you know you are good to go start a conversation. So that's the acknowledgement. Now, when we think about this in the terms of ports, now port is a item that can be opened on a machine. It's a way to communicate with certain protocols. For example, if you think about HTTP, that's over port 80. If you think about HTTPS, that's over port 443. There's a lot of different protocols, and there are 65,000 plus ports that can utilize these protocols. So everything related here has to do with these ports. Now, let's say that you want to connect to port 443 on a website. You're going to send out a SYN packet to that website. You're going to say, hey, I want to connect to you on port 443. And if 443 is open and available for connection, they're going to say, hey, you can go ahead and connect to me. And when you want to actually establish that connection, you're going to send that acknowledgement packet back. Now, let's make more sense of this. Let's go ahead and open up a tool called Wireshark. So this is built into Kali Linux. I'm just going to type in Wireshark, and I'm going to provide an ampersand here just so I have shell access if I need it in the background. And all I'm going to do is capture packet data. So this is going to be listening in on my NIC, and it's going to say, hey, what's he doing? Let's capture all that data. So we're going to capture that. I'm going to start a capture here. You're going to start to see a bunch of traffic coming through. You can see the different protocols here. You can see UDPs coming through right now. But we're going to go establish a TCP connection. So let's go out to the World Wide Web. And I've got Google up. I'm just going to refresh Google. You're going to see a lot of traffic start coming through. So I'm going to go ahead and just stop this right here. Look at all the data packets that get sent when you're using your computer. This is what's going on in the background. You don't even think about it. So we could see some syntax there. Those are in the gray. Let's see if we could find a good one. Okay, so here is one right here. So what we're going to do, actually, let's find a better one. So we're going to come down to here, and we're going to say, okay, so here we are. We're our source IP. This is 192.168.57.139. We're going out to destination of 74.125.21.155. We're saying, hey, I've got this port here. I want to connect to your port. So port 443, this is a web page. We're sending a SYN packet. If that port is open and available for connection and communication, what's going to happen back is that IP address is going to say, hey, here I am. I'll allow you to connect on this port. And if we make that final connection, we're going to go ahead and send the ACK packet back, which is right here. It's going to say ACK. So that is the three-way handshake. Please do remember this is going to come back into play when we get into scanning, and we'll talk about stealth scanning and how we modify the three-way handshake to actually do some scanning. So that is it for this lesson. I will catch you over in the next one. All right, so before we go into the OSI model, I do want to talk about some common ports and protocols. Since this is a refresher, most of these should be pretty familiar to you. I'm going to run through them pretty quickly and just talk about them briefly on each of these common ports. And the reason I've listed these is because there are things that we'll see quite often as a penetration tester, and it's just something that as we're going through the course, if one of these show up, it's something that just rings a bell, and you see a scan, it comes back and you see port 21, you just think, ah, yes, FTP. Or you see port 80, you think, ah, yes, HTTP. So you got to start training your mind to memorizing these ports. So when we get into our scanning, which again, we haven't covered scanning, but when we get there and we see what ports are open on a machine, we're going to be able to have these common ports memorized. So on the TCP side, we've got FTP. FTP is the file transfer protocol. You're going to see this in some assessments. You're going to see this a lot when we do something called capture the flag, where we run through some test machines. You'll see FTP open quite a bit. So FTP, file transfer protocol, all that means is we can log into this server, we can put a file, or we can get a file off the server. Now SSH and Telnet kind of play hand in hand. Telnet is the ability to log into a machine remotely. Now, SSH does the same thing. The only difference is SSH is the encrypted version of that. So with Telnet, you are in clear text, and with SSH, you are encrypted. Now, SMTP, POP3, and IMAP all relate to mail. We're not going to worry too much about mail in this course, but you might see it come back up at some point. So just remember your 25, 110, and 143. DNS. So DNS is a way to resolve IP addresses to names. And we could take a quick look at that if we go back to our Kali machine and say we're at Google here. We've got Google up, But the computer doesn't really know what Google is. The computer is just using nice text like google.com for us, the humans. What's going on the back end is Google actually resolves to an IP address. Now, that IP address is how the computer knows to get back and forth. Because we don't want to sit there and type in IP addresses, this DNS or domain name system has been implemented for us. So we type in google.com. On the back end, it knows, hey, I want to go out to 179.10.22.34, whatever it is in reality. But this is just a quick way for the computer to relate to a human and the human to have easily readable access to some of this stuff. So going back to our PowerPoint, we have HTTP and HTTPS. That is a website, just what you saw there. Mostly everything is on 443 now, or HTTPS. The HTTP on port 80, you'll see sometimes. Remember, that is the non-secure version of the protocol. So HTTPS is encrypted, HTTP is not encrypted and not secure. So lastly, SMB ports 139 and 445. Originally, it was just 139. In the later versions of Windows, they put on 445. You're going to see these ports a lot. This is probably the most common port you're going to see as a pen tester. These relate to file shares. You might also hear this called Samba. So there are a few names for it, but when you think of SMB and you see 139 or 445, think of file shares. And as a pen tester perspective, you got to think about all the crazy exploits we've had regarding SMB. The most recent one as of this course was the WannaCry virus, right? So you had the WannaCry virus. It's also known as Eternal Blue, was what it was built off of, or MS17010 was the official term of that exploit. That exploit utilized an SMB exploit to navigate through networks. So it became very vicious very quick because SMB is opened so frequently on networks. Now, on the UDP side, we also have DNS over here. DNS is both a TCP and UDP protocol. We also have DHCP. Now, when it comes to IP addresses, DHCP associates you with an IP address kind of at random. Now, you could have the opposite of that is what is a static IP address. So with DHCP, you plug into your network, say your home network, and the internet just fires up. Guess what? Probably DHCP on the back end. It just picks a number between a range, says, hey, here's your IP address. I'm going to let you lease that out for 8 hours or a day or a week or however long the timing is set for, and that IP address is yours. Now, the opposite of that, again, is static. So you could say, hey, I want a static IP address, and anytime I plug in with this specific computer, go ahead and give it this IP address. So how are we going to know that? Most likely the MAC address, right? So from layer 2, it's